Hi everyone, welcome back. So for today's video, we're going to look at section 2.2 in our textbook for Precalculus, which involves looking at some average rate of changes. We're also going to go through, so feel free to follow along in the textbook, secant lines, local maximum minimum functions, and then if we have time, even and odd functions. Okay, so we're starting with average rate of change. Let's take a look at my iPad screen. All right, so average rate of change is really important to understand because it comes back in calculus and it's a key part of understanding the derivative, which is an important part of calculus if you choose to take calculus. Start off, and again, this is section 2.2 in our textbook, section 2, chapter 2 in our textbook. And to start off, we're looking at average rate of change. Average rate of change has to do with finding over a set domain, finding how much on average our function is changing over that domain. So an example of average rate of change is, let's say you're taking a road trip, but you have to take a few detours and turn backwards at a few points, and it takes you a lot longer than you expect. And let's take a look at a graph of your trip. So on the bottom here, let's do time. On the top, let's do distance from your house. And let's say you start at your house, and then over time you get closer, and then you get farther away, and then closer, and then farther away. And so on. You have to turn around a lot. So you end up with this kind of weird wavy graph. And then finally you end up overshooting and coming back to your destination. Okay, so here we have a lot of waves, and what we want to figure out at this point is, on average, how long did it take us to get to our destination, or what was our average speed over a certain time. So maybe after 1 minute, you want to see how long it took you to get to your destination, which was at, you want to see how far you traveled between 1 minute and when you got to your destination, which we could say 10 minutes. You know it took 10 minutes total, but at 1 minute, what distance did you travel in that time? So to find this average rate of change, what we're looking for is we're looking for the slope of the line that passes through these 2 points. So we have our orange line here passing through our 2 points. And to find our average rate of change, we're looking for the slope of this line. And we actually have a special name for a line like this. This is called a secant line. So quick definition, a secant line is a line that passes through the graph that we're looking at 2 or more times, so at least 2 times. So as you can see here, it passes through quite a few times, but at least 2 times it's passing through these 2 points that we're looking at. Okay, so finding average rate of change, let's say, looking back at our graph, that after 1 minute you were 1,000 feet away from your house, and then after 10 minutes you finally got to your destination, which ended up being about, let's say, 10,000 feet away from your house. It's in feet. Okay, so this should look familiar for you, where we have 2 points on a graph and we're trying to find the slope of the line that passes through those 2 points. What we can use here is the slope equation that we learned in algebra. 2 points on a graph, finding the slope of the line that passes through those 2 points. We can identify that by looking at our 2 points, x1, y1, x2, y2, and then our slope equation tells us that the slope is going to be the change in y over the change in x. So change in y over change in x, we could take, and it doesn't matter which one we start with, 2 or 1, as long as the order is the same in the numerator and denominator. Let's do y2 minus y1 over x2 minus x1. So here, 10,000 minus 1,000 over 10 minus 1, which gives us 9,000 over 9. So we end up with 1,000, it looks like this is feet per minute, on average, traveling between those 2 points on our graph. So after 1 minute, you traveled on average 1,000 feet a minute to end up at your final destination after 10 minutes. Okay, so when I point out that it's a slope equation, it seems kind of easy, kind of simple. So keep that in mind whenever you're asked to find the average rate of change between 2 points. We're just finding the slope of the secant line that goes through those 2 points. Okay. And I was blocking the 1,000 feet per minute down there. Sorry. Still getting used to this format. Okay, 1,000 feet per minute is our answer for this average rate of change. So finally, to wrap up this topic, when our textbook talks about it, instead of using y, so up here we have y1 minus y2, our textbook uses function notation, and it's looking at two x values. So let's say our input values are x and c, or the two x values that we're looking at on our x-axis. So the output values it talks about are f of x and f of c. Okay, so it ends up doing f of, I think it does x first, f of x minus f of c over x minus c. So same idea, just using function notation. Okay, so we might also be asked to find the average rate of change between a point on our graph, for example, an x value 1, and any other x value. So just an undefined x. And we'll end up usually with an equation in that case. So sometimes we're asked to find the average rate of change between some given x value. Let's say x equals 1 and x, some undefined x. So that way we could find this equation and then really quickly average rate of change between 1 and 3. We just plug in 3 for x into our equation. We can find the average rate of change. Plug in 4 for x. We can find average rate of change. So we don't have to go through the entire process if we're looking at x equals 1 more than once. Okay, so to do this, what we're doing is using the same equation, using f of x minus f of c over x minus c. And the c value in this case is the value that they give us or provide to us. So in this case, we're looking at f of x minus f of 1 over x minus 1. So this is how we can find the average rate of change between x, any x value, and 1. A quick example of this using an equation, because previously we just had a graph, a wacky graph we were looking at. We could use the equation f of x, scroll down a little bit, f of x equals 2x squared minus 3x. Okay, so we're finding the average rate of change between 1 and x for this f of x. So what we're doing is plugging that in to the top there. F of x is going to be 2x squared minus 3x. So we're just plugging in the equation without inputting any x values. So we have that, and then we're subtracting f of 1. And when I fill out f of 1, I'm going to put parentheses here just to make sure we subtract the entire expression. So 2 times 1 squared minus 3 times 1 all over x minus 1. So that denominator has not changed. Okay, so continuing along down here, we can simplify. We have 2x squared minus 3x. And then we end up with minus, we have 2 minus 3, so we end up adding 1 over here, all over x minus 1. Okay, so we figured out our numerator, our denominator. Finally, our last steps are to simplify as much as possible, and we can use what we learned in Algebra 2 to help us out here. So we have a quadratic on the top, and we can rewrite that quadratic as, by factoring it as 2x minus 1 times x minus 1 all over x minus 1. Okay, so there we go. Okay, so we have simplified. As you can see, we end up with an equation. We still have x in our equation, which is fine. And the reason why we factored was to see if we could cancel anything out. And as you can see, we can cancel out the x minus 1s. So our equation, the average rate of change between 1 and any x value is 2x minus 1. So again, this is helpful because if we're asked to find average rate of change between, let's say, 1 and 8, what we can do is use this equation here, average rate of change between 1 and 8. Well, the x value that we're entering is 8, so that's going to be 2 times 8 minus 1. So 15. So 15 is the average rate of change between 1 and 8. In other words, if we were to graph this function in between x values of 1 and an x value of 8, the slope of that secant line is going to be 15. So when we're asked to find the rate of change between a given x value and any x value, we just plug in the x value that's given, and then we simplify from there. Okay, so next up, we're going to take a look at increasing and decreasing functions. All right, so moving on to increasing and decreasing and constant functions, or rather intervals for these functions. Increasing, decreasing, and constant intervals. Okay, so given a graph of a function, it's important that we can identify where the graph is increasing, where the graph is decreasing, and where the graph is remaining constant. And looking at a graph, this might be apparent for some graphs, but we still want to formally go through and define this just because it will get more complicated later on. Let's take a look at an example graph to start. So here, let's actually do 4 quadrants. Let's say we have a graph like this. We have a line, then we have a horizontal line, and then our graph ends up stopping here and then going down, kind of like a parabola. And let's say we have -2 here. Here we have +3, and then this y value is going to be. So when we're looking at increasing or decreasing, we're looking from left to right. So we're going to start looking at this edge of our graph and then moving to the right to see how the y values, or the outputs, the f of x values, are changing. So to start off, I'm going to define these and talk about these just kind of like plainly, and then we'll formally define them mathematically. To start off, as you can see, going from left to right, our function is going up or increasing all the way until we hit -2. So just talking about this, by describing the graph, we can say our graph is increasing till x equals -2. Then we can see that the y value, or output, is not changing at all until we hit 3. So our graph here is constant from x equals -2 to x equals 3. Finally, you can see that the output values are getting smaller and smaller, or more negative and more negative as we go to the right from 3. So our graph is decreasing from after x equals 3. Okay, so looking at a graph, we can kind of identify pretty easily where our graph is increasing, constant, and decreasing. I want to next talk about how we formally define the terms, increasing, decreasing, and constant, using our definitions from the book. So our definitions might seem a bit wordy at first, but stick with me. We will go through and explain what the different parts of these definitions mean. So let's start by looking at our definitions from our book. Our book tells us that a function f is increasing on an open interval I, so they're calling the interval I, if for any choice of x1 and x2, both of which are in our interval, contained within our interval I, with, and they just specify our x1 value is going to be less than our x2 value. So x1 is to the left, x2 is to the right. We have f of x1 is less than f of x2. Okay, so we have a lot of words here, but when we break it apart, it isn't too complicated. So our function f is increasing on an open interval I. An open interval I just means we're setting some domain. We can think about it as a domain or an interval of x values on our graph. So if we take a look at a graph, we could call any interval, let's say, between here and here. This entire interval is our interval I. So just we can think about it as a collection or a restraint on our x values. So interval I, if for any choice of x1 and x2 and I, I'm going to go ahead and just draw a graph here and a line. For any x1 and x2 and I, with x1 less than x2, the outputs can be seen that x1 output is less than the output for x2. What this means is we choose any x1 and x2 where just making sure that x1 is to the left of x2. In other words, we choose two x values. Doesn't matter where they are in the interval. Let's choose one here, x1, and another one over here, x2. And then whichever one comes to the left is going to be what we call x1. So here are two x values, x1 and x2, both contained within our interval I. x1 is less than x2, we can see that. And finally, our definition is saying that it's increasing if the output values are arranged so that the output of x1 is less than the output of x2. So as you can see here, we have our output for x1 on our line, and here we have our output for x2 on our line. F of x1 falls here, f of x2 falls here. So we chose our two x values, and f of x1 is less than or lower on our graph than f of x2. And this kind of makes sense because if we think about it, when we're going from left to right, so this is just saying going from left to right, from x1 to x2, we want to be increasing or going up for our output values. So it's using a lot of words to describe what we saw up here with our example graph. But knowing these words and how to interpret them are important because we're going to be using these kinds of definitions to kind of expand and learn more complicated topics. Decreasing and constant are very similar. We have this same definition. There are just a few differences. So for a function to be decreasing, we're still going to be looking from left to right, so x1 and x2, where x1 is to the left, except we want to make sure that as we go left to right, our output values are going down. So the output value on the left, we want it to be larger than our output value on the right. In other words, if we choose an x1, x2 on our graph, let's say our graph is this line, then we want to make sure that the output values are going down, f of x1 down as we go to the right, to f of x2. So decreasing is similar. We just switch that inequality. Finally, constant is saying for any two x values, our outputs have to be equal. So for constant, the x values have to be equal. So looking really quickly back at our example graph, we can see these definitions in work. To the left, we are increasing because we can choose any x value. Like over here, let's choose x1 and another x value on this interval, x2, and we're going up. For constant, we can choose any two x values along this horizontal line. And as you can see, our y values, our outputs, are not changing as we go from left to right. Finally here, to the right of 3, we can choose any two x values. And as we go left to right, our outputs are going down. Okay, and finally, when we describe increasing, decreasing, constant, we can use terms like this. We can also talk about them using interval notation. So it's increasing for the interval x is less than -2. And then for constant, x is constant in between 3 and -2. Sorry, our function is constant for x values in between those two numbers. And then finally, for decreasing, our function is decreasing for x values greater than. And one final note, this word open is important. So an open interval means that when we look at an interval, like the interval we defined down here, we're not including these endpoints. So we're not going to count these endpoints here. And that's why, looking up here, I don't have an equals or equals to sign. We're not including these here and here. So open intervals just means less than or greater than, strictly without the equal sign.